This is Bob Calcutta, and this lesson is the OR rule for probability. So let's start by looking at an example. We're going to select a card at random from a deck of 52. So we can talk about that sample space. Since we are selecting a single card from that deck of 52, each one of them is equally likely to be selected. We want to know the probability of selecting either a diamond or a heart. So find the probability. Of selecting either a diamond or a heart. Well, again, 52 cards, 13 diamonds are in the sample space, 13 hearts, 13 clubs, and 13 spades. What is going to be important, especially later in this discussion, is you cannot be both a diamond and a heart at the same time. So we have our entire sample space, 52 possibilities. Our probability of diamond or heart, how many winners do we have? We have a total of 26 out of how many total out of 52, which could reduce to 1/2. So that's fine. But there's something else for us to notice. The probability of being a diamond, how many diamonds do we have? 13 out of 26. How many hearts do we have? Also 13 out of 26. So you'll notice in this case, the probability of diamond or hearts is just the probability of diamonds plus the probability of hearts. Diamonds or hearts is the probability of diamond plus the probability of hearts. Is that always the case? Well, not really. We'll look at the next example when that's not the case. So diamonds or hearts, again, in our situation here, 13 out of 26. Plus 13 out of 26. 26 out of 52, or 1/2. The thing to remember here is you cannot be both a diamond and a heart at the same time. So what we would say is we would say diamonds and hearts are mutually exclusive. So the next example will not be. So let's take a look at another one, and then we'll generate a rule from that. So our experiment will be the same. We're going to select a card at random from a deck of 52. So R will be the event that what we have is a red card. And K will be the event that it is a king. Now let's think about how many red cards we have and how many kings we have. So red cards, our sample space, again, S, is all 52. So we could list those out again. 1 of hearts, 1 of diamonds, 1 of clubs, 1 of spades, 2 of hearts, ... etc. So we have 52. How many red cards do we have? How many red cards do we have? Well, all the hearts, all the diamonds. So 1 of hearts, 2 of hearts, all of the hearts, all of the diamonds, 1 of diamonds, 2 of diamonds, all of those. How many are there total? There's a total of 26 red cards. Again, 13 hearts, 13 diamonds. K is our event kings. Well, what are our kings? If we call our event K, we have the king of hearts, the king of diamonds, the king of clubs, and the king of spades. So there are 4 king cards. So we can look at the probability of red. We can look at the probability of king. Probability of red is 26 out of 52. I'm going to choose not to reduce the fraction. Probability of king is 4 out of 52. But what about the probability of red and king? Excuse me, red or king. What's the probability of red or king, which is what I want? Probability of red or king. How many do we have in that set? Is it 26 here and 4 there? Is it that simple? Or is it more complicated than that? Now, these are not mutually exclusive. Red and king are not mutually exclusive sets. So this is going to behave differently. Why are they not mutually exclusive? Because we have cards that are in both groups. The king of hearts and the king of diamonds are in both groups. If we have overlap, then the 2 sets are not mutually exclusive. So we've got to think about how this is all going to fit together. How am I going to get the probability of red or king? What am I going to do to get that? So again, let's go ahead and think about what we have here. Our red set, 1 of hearts, 2 of hearts, all the way to the end, 1 of diamonds, 2 of diamonds, all the way to the end. Our king set, king of hearts, king of diamonds, king of clubs, king of spades. So who do we have in the red or king group? R or K group. That's what we're interested in. Who is in the R or K group? Well, everybody we had in the R group, so all 26 of those guys. So 1 of hearts, 2 of hearts, 1 of diamonds, 2 of diamonds, all of those. And then once we're through all those, we also have 2 other ones that are not in that group. What do I have in the king group that was not already counted? Well, king of hearts was in this first group. King of diamonds was in the second. So king of clubs and king of spades are added in. So think for a second, how large is that red or king group? If we're going to ask just for the total number of winners divided by the total possibilities. Probability of red or king is how many total? 26 here plus 2 more. That will give us 28 out of 52. Now, can we develop that as a rule? Can we develop that as a rule? And the way to think about this is to think of a Venn diagram. And look at these regions. This is red cards. This is king, and this is overlap. Now we have a total of 26 red cards. How many are not kings? 24 are not kings. 22 of them are kings. How many kings do we have? We have 4 kings. 2 are red and 2 are black. 2 are not. So you can see there's your 24 plus 2 plus 2. There's your total. But if we can put all this together, the probability of red or king is the probability of red. So we've counted those 2 sections, plus the probability of king. We've counted those 2 sections, but we've counted the overlap twice, minus the probability of red and king. And that will be our general rule for OR situations, for unions, is probability of the first event plus the probability of the second event minus the overlap. So in our situation here, we saw before there were 26 total, right? For our red cards, there's 26 total. For our king cards, there are 4 total. But for our overlap, how many do we have? Again, king of diamonds and king of hearts are both red and kings. So to use our rule here, we're going to say 26 out of 52 red cards plus 4 out of 52 king cards minus the overlap minus 2 out of 52. 26 plus 4 is 30 minus 2, 28 out of 52. Is our probability of choosing either a red or a king card, which you'll notice agrees with what we said when we just listed our total number of possibilities. So let's go ahead and state our rules. We have 2 rules, 2 OR rules, one for a mutually exclusive case and one if they're not mutually exclusive. And I'll jump to E's and F's this time. OR rules for probability. So the probability of E or F equals probability of E plus the probability of F when E and F are mutually exclusive. So I could ask for, in our first example, we said diamonds or hearts. You cannot be both diamonds and hearts. Those are mutually exclusive events. That's what that enabled us to use that version. But if they're not mutually exclusive, in general, the probability of E or F is the probability of E plus the probability of F minus the probability of E and F. So that's our case when red and kings come into play. They cannot be said to be mutually exclusive because we have 2 cards that are in common to both. Now, in reality, if you have mutually exclusive events, this rule still works. If E or F, E, F not mutually exclusive, well, probability of E plus the probability of F, the overlap would just be 0. So if you're going to memorize one rule, this would be it. Just to clarify, there's another notation that we use in set notation. OR is equivalent to union. So we could say the probability of E union F is the probability of E plus the probability of F minus the probability of and is intersection E intersect F. So that's another notation that we can use. All right, let's take a look at a set of grades from various classes. And then we'll try to answer some questions about these. So here we go. We've got students at a high school take either Algebra 1, Geometry, Algebra 2, Pre-Calculus, or Calculus. And I could ask the following question. And let's say every student is just in one math class. So every student isn't in a math class. Every student gets a grade. So if I could ask the following question, if G is the event that a student is in geometry, and C is the event, maybe I shouldn't use C, maybe P is the event the student is in pre-calculus. I could ask, what is the probability of G or P? And no student is taking both classes. Okay, so a student is either in geometry or in pre-calculus. We're not going to ask a high school student to take 2 math classes. So that would simply be probability of G plus the probability of P. Maybe we'll make it PR for pre-calculus. Because they are mutually exclusive, so how many students are in geometry? In geometry, we have 22 out of 101. Plus how many are in pre-calculus? Let's say we have 18 out of 101. 22 and 18, it would be 40 out of 101. So again, geometry and pre-calculus, no student is taking 2 math classes. Therefore, they would work in terms of using the mutually exclusive version of that rule. Now, if instead I ask, what is the probability that a student gets an A or is taking geometry? So this time we'll say A is the event, student earns an A. G is the event that the student studies geometry. So you certainly can both study geometry and get an A. We've got these people right here are in the geometry group and in the A group. So there is an overlap. They are not mutually exclusive. So if that's the case, we're going to use our OR rule. Probability of A or G will be the probability of A getting an A plus the probability of G studying geometry minus the probability of A and G, because those people would have been counted twice. So how many people are in the A group? A group, 37 out of 101. Plus how many are in the geometry group? 22 out of 101. Minus how many are in the overlap group, both in the A group and in the geometry group, because they have been counted twice. In the A group and the geometry group, there are 5 out of 101. So we've got 37 plus 22 minus 5. What does that give us? 37 plus 22 minus 5 gives us 54 out of 101. So again, just to clarify one last time, let's take a look at our 2 rules. Our OR rule for mutually exclusive case and the general case. So what do we say? Probability of E or F equals the probability of E plus the probability of F when what is true? When those events are mutually exclusive. When they don't overlap, when no element of the sample space is common to both E and F simultaneously. And then our other version is, in general, probability of E or F, probability of E plus the probability of F minus the probability of E and F. But if they are mutually exclusive, the probability of E and F is just 0. So in reality, this general rule works for everything. And again, one final note, if you see this in set notation, we could replace or with union, we could replace and with intersection. And it can also be written as probability of E union F is probability of E plus probability of F minus probability of E intersect F. And that will conclude this lesson.